So we're continuing our look at the chemical basis of life with some really important ideas in this presentation that relate to water. Water is essential for life as we know it. In fact, living cells are anywhere from 70 to 95% water. Life exists in watery solutions. And water, being a polar molecule, has some very interesting properties, what we call emergent properties that result from the interactions between water molecules. One of these interesting properties is that the hydrogen bonding between neighboring water molecules causes it to be a very clingy substance. And there are some specific emergent properties relating to this cleanliness. And one of them is cohesion. Water is cohesive. Because water molecules stick together, a volume of water tends to act as a unit. And the smaller that volume of water, the more cohesive it is, and the more important that property becomes. Water also exhibits surface tension. So at the surface of a body of water, the hydrogen bonds creates sort of a surface film that can even bear weight. And there are entire communities of organisms that exist on that surface tension. Water is also adhesive, meaning it sticks to surfaces. And we'll see in a moment here some important examples of how cohesion and adhesion work together to help plants transport their fluids. This is part of a community of creatures that make use of the surface tension of water. That is called a water strider, or sometimes it's called a pond skater. And notice how its legs do not break through the surface of the water. There are dimples. Its weight is so small that it is being borne on top of the water. It is walking on the surface of the water without getting its feet wet. There are other invertebrates. Your textbook has a picture of a water spider doing the same thing. Next to it, we see some little duckweed plants that also exist on top of the water and make use of that surface tension. This figure focuses on how plants transport water and things that are dissolved in water up. There is a tissue in plants called xylem that conducts solutions up from the roots to the leaves. Unlike us, plants don't have a heart to pump their fluids. They have to rely on passive mechanisms. And key to this is the cohesion and adhesion of water. Within xylem, the water molecules form a chain, and there's basically a standing column of water, and that acts as a unit. And any forces placed on that column of water will cause the whole column to move. And the column doesn't tend to backslide because it adheres to the cell walls of the xylem. At the leaf end, evaporation causes a drop in water potential that pulls fresh water up from the roots. So this column of water is constantly being pulled up from the top, and all the water molecules form a chain. They stick to the next, they stick to the walls of the xylem. It's a very effective mechanism to transport fluid without a pump. There are two important emergent properties of water that has to do with heat and temperature. And the first is specific heat. Water has a high specific heat. Specific heat is defined as the amount of energy needed to cause 1 gram of a substance to increase in temperature by 1 degree Celsius. We measure specific heat in calories. A calorie is actually defined as the amount of energy needed to raise a gram of water by 1 degree Celsius. So compared to many other liquids, water has a high specific heat. It takes a lot of energy to make it change temperature. That's really important for the maintenance of internal body temperatures for organisms like us that have a lot of watery fluid. It also means that bodies of water, lakes and ponds and rivers and oceans, can be thermally stable over long periods of time because of the amount of energy needed to change the temperature of water. You can go outside in the summer in the morning, and let's say it's 70 degrees, and by noon it's 90. The air has experienced a 20-degree temperature change, but a local pond or lake will scarcely change temperature at all over the course of that one day. So aquatic creatures can enjoy thermal stability. Water also has a high heat of vaporization, and that is the amount of energy needed to get liquid water to change into a gaseous state to vaporize. So when water does evaporate, it takes a lot of heat energy with it. Evaporative cooling is a really efficient mechanism that lots of organisms use, like humans, to cool our body, right? So when you sweat and that sweat evaporates, cools you off. So high specific heat and high heat of vaporization are important properties of water. Now, water exists commonly in 3 states of matter, right? Solid, we call it ice, a liquid, or a gas. That is not unique. There are other substances that commonly exist in all 3 states of matter. But with most substances, when you change it from its liquid to its solid state, it gets more dense. The density increases. However, with water, there's something else going on. In liquid water, hydrogen bonds are constantly being broken and reformed, and water molecules are jostling around, right? But when water freezes, the hydrogen bonds stabilize, it assumes a crystalline structure, and on average, the water molecules are pushed farther apart. And because the molecules are farther apart, the density decreases. Water becomes less dense in a solid form, and therefore it floats. Now, that is important because if ice was more dense than liquid water, we would see water sink as it froze, and bodies of water in cold environments would freeze completely solid. As it is, though, ice forms on the surface and accumulates at the surface and will eventually buffer the water below so that the water below the ice is relatively warm compared to the atmosphere. Look carefully at this picture. This is a frozen pond, and can you see the snapping turtle, right? He was lumbering around under the ice, right? It's liquid under there. This was a very cold day. It was below 0. And that water below the ice is above freezing, right? So there's a huge temperature differential there. As water froze, the ice got thick and insulated the water below, and that turtle is surviving under the ice. Now you might think, hey, doesn't have a problem because turtles breathe air, right? How it's going to breathe? How will it breathe? Well, the turtle has a couple things going for it. Turtles are ectothermic, or so-called cold-blooded. So its body temperature is very low, and its metabolism is low, and its oxygen demand is low. Also, these highly aquatic turtles, like the snapping turtle, they can actually pump water in and out of their butt and get oxygen out of the water. They use their vascularity of their butt sort of like a gill, right? So there's butt breathing turtles. That's your fun fact for the day. Water is said to be the solvent of life. Now, to understand that, there's a little bit of terminology we should cover. A solution is a liquid which is a uniform mixture of two or more substances. The first of these substances is the solvent, and that is the agent in which the other thing is dissolved. And we're saying water here is an excellent solvent. The solute is the substance that is being dissolved. So many biologically important molecules dissolve when you put them in water. Water is the solvent of life. One of the things that makes water such an excellent solvent is its polarity, that it has positive and versus negative poles. When you put a substance like salt in water, it ionizes. The ionic bond between sodium and chlorine breaks, and water molecules come to surround these ions. So the partial positive ends, the hydrogen end of water molecules, will surround the negatively charged chloride ions, and the relatively negative oxygen ends of water molecules come to surround the sodium ions. What calls this a hydration shell, this sphere of water molecules that surrounds the ions, keeps them in solution, prevents them from reforming an ionic bond. So biologically important things dissolve well in water because of the polarity of water. The last few topics we'll talk about in this presentation relate to pH. pH is really biologically important. The pH of a solution can affect the shape of molecules. It can affect the availability of ions. It can affect important metabolic processes. So all organisms have an optimal pH for each particular chemical reaction. pH is a measure of hydrogen ion concentration. That's what we're measuring when we test the pH of something. In lab, we can use pH meters. We can use pH sensitive test paper. We can use pH indicator dyes, right? Solutions that will change color under different pH environments. pH is the negative log of hydrogen ion concentration. So it is a logarithmic scale in the base 10, and what we're actually measuring again is the concentration of hydrogen ions. Now, in discussing pH, the terms acid and base are used. An acid is a substance that causes an increase in the relative hydrogen ion concentration. Base, on the other hand, is a substance that causes a decrease in the relative hydrogen ion concentration. So we have a numeric pH scale. right? We quantify that hydrogen ion concentration and express it numerically. Our scale ranges from 0 to 14. Below 7, all the way up from 0 to 6.999, that end of the scale, solutions are said to be acidic. And remember, we're talking about the relative concentration of hydrogen ions. So in an acidic solution, there are more hydrogen ions than there are hydroxide ions. That's the OH minus, right? So it is a situation where hydrogen ions are more numerous in the solution than hydroxide ions. In a basic solution, you're above 7 all the way to 14, and there are more hydroxide ions than hydrogen ions. So by affecting either hydrogen or hydroxide ions, you can affect pH because you're affecting the relative concentration of the two ions. The neutral point in our pH scale is 7. That is the point where the concentration of these two ions are in equilibrium. Hydrogen ion concentration equals hydroxide ion concentration. So here's a version of the pH scale from chapter 2 in your textbook. And we see pure water, pure distilled water. The concentration of those two hydrogen and hydroxide ions are equal. On this particular example, if you go up in the scale closer to 0, we have an increase in the hydrogen ion concentration. It is becoming increasingly acidic. So keep that in mind. As you go down numerically, you are going up in hydrogen ion concentration. And this is a logarithmic scale. So at pH 5, for example, there are 10 times as many hydrogen ions as pH 6. As you go up numerically, you go down in hydrogen ion concentration, right? So as the pH number gets higher, the hydrogen ion concentration is decreasing. So here's a simple graphic you might find useful. The pH scale, again, ranges from 0 to 14. And what we're talking about with pH is the relative concentration of hydrogen ions. Notice the diagonal splitting this figure into two triangles, right? The area below the diagonal represents the concentration of hydrogen ions, whereas the space above the diagonal represents the concentration of hydroxide ions. So as you go down numerically, hydrogen ion concentration increases. As you go up numerically, hydrogen ions decrease relative to hydroxide ions. And then at pH 7, we have a point where the two are in equilibrium, right? The concentration of the two are equal. So I mentioned there are many ways of testing pH. We have quantitative ways using pH meters. We have qualitative ways using pH sensitive dyes. Next, I have a real short video I recorded demonstrating one of these dyes. This is an interesting pH indicator dye called phenolphthalein. At about pH 8.2, it undergoes a dramatic color change. I can tell now from the absence of color that the pH of this solution is below 8.2. If I add a drop of sodium hydroxide, it should elevate the pH and hopefully trigger that color change. So the pH goes up, the molecule changes shape, it undergoes a rapid color change. Ooh, I need another drop to keep it there, right? So I also want to demonstrate how the pH of the air you exhale can affect the pH of water. All right, so what's going on here is the carbon dioxide in my breath combines with the water inside the solution to form carbonic acid, which is H2CO3. And that carbonic acid ionizes, it breaks up to release hydrogen ions and bicarbonate ions. And it's that buildup of hydrogen ions that causes the pH to drop and causes the color change.